So for helium, it's easy enough to write up explicitly for only 2 electrons all the different possible wave functions we could have, and then look at it and see, oh, this one's antisymmetric, this one's symmetric. But when we get to larger atoms, say even up to beryllium, boron, right, up to larger elements, how do we make sure that we get antisymmetric wave functions? Because this is a fundamental property of the particle. If we write wave functions that represent them, they have to satisfy this constraint, or else they're not proper wave functions, and they're not going to give us correct answers if we use them for doing calculations. And so the way that we do this is what's known as a Slater determinant. So this, again, the whole purpose of what we're about to discuss is ensures we have antisymmetric wave functions with respect to particle exchange. And let me move this. There we go. On my screen, I can't see myself, so sometimes I write where my thing is up in the corner up here. Okay, so if we have, say for helium, we can take what we just wrote and write this as a determinant. So we'll have 1s alpha 1, 1s beta 1, 1s alpha 2, 1s beta 2. Now the property of determinants is that we multiply these two and subtract it from these two multiplied. So we'll get 1s alpha 1 times 1s beta 2 minus 1s alpha 2, 1s beta 1. And this is what we want. This is exactly what we had before, which gives us the antisymmetric wave function. Now, why do we do this with determinants? So there's some properties of determinants that make it really suitable for this. So property number 1 is that if we swap any 2 rows or columns, the sign of the determinant changes. And so this is the property that we're most interested in. If we change the identity of any 2 electrons, it's antisymmetric. And so if we write this as a determinant, we ensure that property that we need for the antisymmetric wave functions that we need for fermions. All right. The second property, and one that's a consequence of all of this, all these properties of fermions, is that if any 2 rows or columns are equal, so if we have, say, the same quantum numbers for any 2 electrons, so if any 2 rows or columns are equal, the determinant will go to 0. So this property says that we can't have any 2 electrons, not possible to have 2 electrons with the exact same quantum numbers in the same system. And this property of electrons is what gives rise to what we know as the Pauli exclusion principle, right? That if an electron occupies a specific orbital, right? Say we have an electron in a 1s orbital. If there's already an electron that's spin up, you can't have another electron that's also spin up in that same orbital. You have to have one that's spin down instead. And so this is what gives rise to the Pauli exclusion principle. So it's fundamentally the fact that electrons are fermions that gives rise to this principle that we use when we're building up atoms, right? When we're adding electrons to atoms. So if we have, so our general sort of way that we make Slater determinants is that we'll have our determinant and we have our different electrons going as separate rows. So electron 1, electron 2, etc., etc. And then we have our different spin orbitals going across the top here. And however many we need, right? Spin orbital 1, spin orbital 2, etc. And the last thing we're missing is normalization. So to normalize, we need to add a factor of 1 over the square root of the number of electrons factorial. All right, so just to give one example of this, and we'll go over some examples when we meet together in class. Let's look at lithium, right? Let's go to 3 electrons. So we need to have, we'll have 1s spin up, 1s spin down, and we're going to need a 2s electron as well, and we'll just pick spin up. It doesn't really matter, we could pick alpha or beta for this example. All right, so our wave function is 1 over square root of 3 factorial, and then our determinant, now across our first row, we're going to have electron 1, and so we'll have 1s alpha 1, 1s beta 1, 2s alpha 1. And then we'll have in the second row, it'll be our second electron, so we'll label electron 2, but the same spin orbitals going across. And then our third row is electron 3. And that forms our Slater determinant for the lithium, and so this is a shorthand notation, right? What we actually end up getting, if we multiply this all out, is we end up with some long wave function that's, products of these single electron wave functions, right, and combinations of them, the specific combination that gives us an antisymmetric wave function. And so you'll get a chance to practice on your homework. We'll also look at this in class. And so this is how we represent multi-electron wave functions with the right properties.